Swayam Prabha. Digital India. Educated India.
So I have this particular inequality where I know that if you sum over all the pieces coming after his piece, which is Vi of Pk, I will get at least this particular value for the subsequent pieces. Okay. So via averaging argument, what can I guarantee right now? Exactly. There must exist, there exists at least one particular piece, at least one piece Pj, where j is greater than I. I mean, like in the subsequent pieces, there will exist at least one Pj such that Vi of Pj is at least 1 by n, Yeah. Why do I have this? Let's say for contradiction, I don't have it. So for contradiction, let's say Vi of Pj is less than 1 by n for all j coming after I, or let's say k, Let's say this is true. If I just sum it up again, Vi of Pk for all k's coming after I, what I'll get is less than n minus I by n, right? There are remaining n minus I pieces here, and all of them are all of them are valued at less than n minus 1 by n, and therefore if you just sum it up, you'll get this. So in particular, there does exist, and this is what we call as an averaging argument. In particular, there will exist at least one particular piece Pj for this agent I, such that he values it again at least at 1 by n, right? Yeah. So in particular, he has at least two pieces for him which are valued at 1 by n. One was Pi to begin with, because he shouted it at iteration I, and the other is, I'll just set, okay, so I'll have a function sigma where sigma of I would be j, which just represents that for agent I, Pj is the piece which he again values at least at 1 by n. Okay, so for each agent I, there are pieces Pi and P of sigma I, such that both of them are valued at least 1 by n. Right? This is clear? Yeah. Also note that the property that sigma I is strictly greater than I, right? Because you found the piece ahead of piece Pi, right? Because you found it somewhere here. So you have sigma I is greater than I for all I in n minus 1. So this holds true for any particular agent, because we started with an arbitrary agent I in the set n minus 1. Yeah. Okay. So yeah, this observation just gives us the result now. So what will happen is, just think of this sigma as a backup scheme, okay? So what happens is, okay, I don't care if, let's say I am agent I, and the secretive agent comes in and he takes away my piece Pi. I don't care, okay, I have a backup piece P sigma I, I'll just go there. But P sigma I would be someone else's. He will go to his backup allocation, and so on, and it will give you a proportional allocation since sigma I is greater than I. I'll be formal in a minute. But just think of sigma as a backup scheme. You have two choices at least. Every agent has two choices at least in the allocation in the n partition here, such that they get value of at least 1 by n from both of the pieces. And also because the backup scheme for an agent I always lie ahead of his primary piece Pi. This is also very important. Yeah. There's no cycling back. Yeah. Yeah. V of. No, wait. V of. Vn minus 1. Pn. Exactly. Yeah, this is the observation. Because he only has just one piece ahead of him, right? So this will definitely be true. Because for all the pieces till before n minus 1, it was all strictly less than 1 by n. For Pn minus 1, it's exactly 1 by n. So ahead also it should be whatever the leftover is 1 by n. Yeah. Yeah. No, just say it again. If anyone, pick. Who is anyone? Okay. Yeah, sure. Because it's unallocated right now. It's not a primary choice of any agent till n minus 1. Yeah. It was a leftover piece after we've done the moving knife procedure. Yeah. So his observation was in particular for n minus 1th agent. Let's just set I equal to n minus 1 for this particular observation. So he had his primary piece Pn minus 1, which he values at least 1 by n, and there exists one more somewhere ahead of it. You only got one option. It should be and it must be Pn. Okay, because sigma I is always greater than I because of this particular inequality. Ahead of what you have cut, there will exist some piece of value at least 1 by n. Right? Yeah. So in particular, this is also true. Right? I hope now some idea is coming to your brains. Okay. Yeah. So again, just a little informally to give you idea what we are doing. So let's say this is P2, this is P3, this is P4, and this is, let's say P5, the leftover piece. And n is equal to 5. Yeah. Yes. 2 by n. Yeah, okay, yes. Oh no, this is a procedure. You have to be like truthful and you have to follow the procedure. You need to make a cut as soon as you reach 1/nth of your valuation. Yeah, there's no manipulation or strategicness coming here. Yeah. It's a, yes, he knows. No, that's again, again, they're not being strategic or they're not being manipulative right now. I know we've seen a lot in matchings and votings, but right now we are not dealing in the strategic aspect of fair division at all. Yeah, they are being truthful in a way. So let's say just for an example or for an illustration, let's say there are 5 agents in the system, and therefore I just have valuations known for just 4 agents. The 5th guy is being secretive. So the 4 agents make such a cut, and this is the leftover piece, which I just call it as P5. So now let's say this particular agent must have a backup scheme, a backup allocation, a backup piece somewhere ahead of it. So let's say this is for agent 1. Let's say it's P2. So basically sigma 1 is 2. Okay, let's say for agent 2 it's P4. For agent 3 it's let's say again P4, and for agent 4 we already know it should be P5. Right? So do you see what will happen for any choice of the secretive agent? Let him pick anything, P1, P2, P3, P4, P5. I'll still be able to allocate the remaining of 4 agents in a way that it will be proportional for them. right? So let's say, I don't know, he picks P1. The secretive guy comes in and say, okay, I just like this piece the best. So what will happen is P1 will shift to, so this will be the allocation. We have not really allocated anywhere yet. We have not given an assignment. So the final assignment would be secretive agent, which is N, goes to piece P1 because he picked it. Agent 1 will shift over to piece 2. Agent 2 will shift over to piece 4. 4 will shift over to 5, and P3, agent 3 gets his piece P3. No one really took it. P3 was not a backup allocation for backup piece for any agent, right? So just for being clear, let's say secretive agent picks piece P1. So what will be the final allocation? So agent 1 will be allocated to piece P2. Agent 3 will be allocated piece P3, right? Yeah. Agent 4, oh sorry, agent 2, I should write agent 2 first. Agent 2 will be allocated what piece? Exactly, P4. Agent 3 is okay, his piece has not been taken away by any other agent, he will just get P3. And agent 4, yeah, since his piece is taken away by someone else, in particular agent 2, he will just get P5. And this is my allocation, and note that it is a proportional allocation, right? For every agent, for secretive agent it anyway is because he chose to pick first. For remaining of agents, since I always am allocating an agent either piece Pi or his backup piece P sigma I, I am sure that they all do achieve proportionality. Yeah. Yeah, no. I understand. We are not just being manipulative right now. But then why P4 will do it? Everyone else will also do some manipulations. I don't know. Yeah. 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 In a way also, okay. Yeah. Okay. Yeah. Yeah. Yeah, again, like it's not trivial to see that we'll have strategy proofness over here. We're not dealing with any manipulations currently. We know the valuations, or let's say the agents are being truthful. Okay, just to note that, okay, we need to make sure that no cyclicity will arise in this particular manner, right? It's not the case that no, every person must be able to get something and no cycles form. It's not the case that P2, agent 2 picks P4 and then P4 says no, I'll pick P3 and there's a cycle going on and you're not able to resolve it. So we'll just say that to begin with only there are no cycles anyway because of the property that sigma is greater than I. So you have a sort of what we say as topological ordering. Yeah. Yeah. So just note that in this particular, since we've reindexed the agents, these arrows which denotes the backup piece, they are always ahead of them and therefore you can't circle back. And in particular, if you just, okay, no, if you have this till n minus 1 and then n, so these are agents, they just, yeah, there are their sigma i's, and this is always, n minus 1 always goes to n, and therefore n is a sink, right? And since we have a sink, there will be no cycles also. Yeah. Since we can, so because of this property, you can induce a topological ordering which is acyclic, and therefore there will be no cycles forming, right? Okay. Yeah. And formally what is happening is, yeah. So formally we need to construct the bijection pi k, right? Remember, for every choice k of the secretive agent, we needed to come up with a bijection, right? So pi k, like, okay, so basically for every choice pk here or ik whatever of secretive agent, we need to construct a permutation pi k, but this is quite simple. What you do is, yeah, so from, if a piece, okay, I should use this. So if a piece k is picked up, you can have a directed path. So a directed path from agent k till n, which is this particular n, and then let's say this directed path denoted by, let's say, sk. So your allocation pi k would be, so you set for all agents who are not on the path, this sk, set it to be I, and then the ones who are on the path sk, you basically shift over them to sigma I. This would be my allocation, this would be my bijection pi k for every choice pk. Yeah. So note that here also, if p1 was the choice of secretive agent, which means that k is equal to 1, I had a path from p1 to p2, p1 to p2 to p4 to p5, right? This was my path from p1 to p5, and p3 was not in the path, and therefore p3 got, agent 3 got his choice p3, and all others got their choice sigma of I. And we have again a cyclicity because of the topological ordering induced by sigma. Yeah. Yeah. I hope this notion of backup scheme or backup allocation is clear to you, right? Yeah. Yeah. Any questions, any doubts? Okay, yeah. So so what is our final result? We are basically proving that in a system, so give me a cake division instance. So where you have n agents, you have the cake 0, 1, but you have valuations only for the first n minus 1 agents. That is your input. In such a case, the previous algorithm which I have described, so there does exist an algorithm okay, which outputs an n partition of the cake let's say, yeah, okay, let me just denote by p again because I've been doing it. So n partition, and note that it is contiguous, right? That is again clear since we did a moving knife procedure and we made n minus 1 cuts, and therefore the partition is a contiguous cake cut for the instance. So which outputs an n partition of the cake such that for every choice, so I am again emphasizing for every choice of the secretive agent pk, where it can be any choice, he can literally pick any piece because he just comes in, picks it and goes away. So for every choice pk there exists a bijection, and bijection is nothing but the one which I just wrote here, this pi k, right? And we constructed this bijection using the backup scheme sigma. So there exists a bijection pi k which basically goes from all n minus 1 agents to, so this n partition minus the piece picked up by the secretive agent or the nth guy. So there exists a bijection such that this pi k induces a proportional allocation, or in other words pi of vi of pi k I. So this is the piece agent I gets, which is being dictated by the bijection pi k. This is at least 1 by n of the whole valuation, which is 1 only. Yeah, or just let me write it. Such that this happens for all agents in n minus 1, right? So even in the presence of a secretive agent, we are indeed able to come up with a secretive proportional allocation. The way secretive proportional is being defined is exactly this. You do the division first and then the secretive agent picks his choice, and the remaining agents are able to accommodate themselves in a way that it is still fair. Yeah. Yeah. And again, the runtime of this particular algorithm is poly. Since we are just doing cut-eval queries, and you can analyze how many cut-eval queries we are doing, it will be poly in n. Yeah. That analysis of counting the queries is similar to moving knife procedure, and therefore it runs in polynomial time. Yeah. Okay. So this is clear. So proportionality in a secretive setting is achievable in poly time with a contiguous cake cut, which is a big thing. Okay. So we also have another result, but I will not at all go into the details of it since I am running out of time, but it talks about secretive epsilon NV freeness. So yeah. So in this particular case, the cake cut can be, let's say, not contiguous, and we are in the setting of non-contiguous, because as we have seen, NV freeness is a difficult notion to compute and to achieve. So in that particular case, we are again indeed able to do the whole thing and achieve secretive epsilon NV freeness, and obviously the algorithm is different, it can't be moving knife. But yeah, so in that particular thing, what happens is everything happens, but at the end what you get is P. So this, let's say this allocation now is some I, which can now be a non-continuous division. So every agent again gets a piece which he values for all other pieces minus epsilon, and therefore it's an epsilon NV freeness. Yeah. So the same thing, we are able to come up with an algorithm which first of all computes a division of the cake, might not be contiguous, such that again for every choice made by the secretive agent, we are still able to accommodate the remaining n minus 1 agents in an NV free manner. And again this J runs over all n, which means that the remaining n minus 1 agents also do not envy the nth agent. Yeah. But here we are able to achieve epsilon NV freeness again in poly time. Remember the difficulty we had in computing NV freeness in the general model, which was not being secretive. Here it's a partial information setting, and again we are able to achieve epsilon approximate NV freeness in polytime. Yeah. So the proof is entirely different, but yeah, this is one thing you can keep in mind. Yeah. Okay. Any questions? I hope the setting is clear, the secretive or the partial information setting. There's a bunch of work in partial information settings. This is one of the works in the literature.